when it comes to natural oscillation, we can still think of many musical instruments that operates basic on natural oscillation. So if natural oscillation take place, the form of energy can be transformed, and the energy can be stay within this resonant instrument or resonant cavity. So the resonance took place depending on the so-called boundary condition. So for transmission lines, there are two important boundary conditions, include the short circuit termination and the open circuit termination. So as you can see from this slide, for short circuit termination, the voltage across the termination must be 0 at all time. Therefore, the currents on that particular position can reach the maximum amplitude. On the other hand, if you have an open circuit termination, then the boundary condition is that the current must be 0 on that place at all times, and therefore the voltage can have the so-called maximum amplitude at the open circuit termination. And as we observe the voltage and current distribution on a short circuit line, which exhibit the so-called completely standing wave, we notice that the nodes, the nuance for voltage nuance and current nuance, as well as the voltage maximum and current maximums, are separated by a distance of a half wavelength. So for the resonance structure, the smallest resonance structure is in the form of quarter wavelength resonant mode, and it requires one end to be open terminated, and the other end is short terminated. Therefore, the true boundary condition on both ends of the on the two ends of the transmission line can support the so-called quarter wavelength mode. And as you already noticed, for one end open, one end short transmission lines, the higher order modes follow the order as 3 times of the 3 quarter wavelengths, 5 quarter wavelengths, 7 quarter wavelengths. So the frequency correspond the structure will be odd multiples of quarter wavelengths, and the frequency will multiply as odd integers of the fundamental mode. So if the fundamental mode frequency is f, the next one will be 3 times f, and the next one will be 5 times f. So we can continue in this manner and see that any standing wave pattern for which the length of the line is an odd multiple of 1 quarter wavelength. So you can express the length, the relationship between the length and the wavelength in equation 7.9. So they are all, they can support the resonance, fundamental and higher order mode resonance on that line. And this equation can be modified, can be massaged a little bit. So basically this is the same equation. So if you massage that equation a little bit, you can express the wavelength of those modes in terms of the length. So as you can see, when n increases, when n increases, the wavelength will become smaller and smaller. And the same thing can be you can also derive the expression for the resonant frequencies, which is simply the division of the propagation velocity Vp over lambda n. So you substitute lambda n with equation 7.10, and you end up with the resonant frequency expression. And if you substitute n with 1, 2, 3, and you will find that higher order mode frequencies will be at multiples of the fundamental frequency. And all these frequencies are known as natural frequency of oscillation 自然共振所以在共振或者我们讲自然共振里头尺寸是最重要的尺寸最重要的。The standing wave pattern are said to correspond to different natural mode of oscillation. The lowest frequency is known as the fundamental frequency of oscillation. So let's review some of the important definition of the terminologies we have are pertinent to natural oscillation. So the lowest mode is referred as the fundamental frequency of oscillation, or the fundamental mode. And the quantity n, as you see in the previous equation, is referred as the mode number. 模态的那个数字啦And for non-sinusoidal voltage and so this statement expresses the that non-sinusoidal voltage and current distribution on the line can be represented as superposition of some or all the infinite number of natural modes. Okay, so which means for an arbitrary signal, you can synthesize, you can synthesize this arbitrary signal using fundamental modes. So, which pretty much, well, you already know that because any arbitrary function can be represented as an infinite sum of sinusoidal signal 嘛所以任意的波形可以用不同模态的那个不同模态倍率的 cosine function 来去组合而成嘛And natural oscillation also occurs on line, short circuit on both ends or open circuit on both ends. Okay, so the very last sentence introduce the other kind of natural oscillation that I have drawn on the blackboard. Okay. So now let's move on to the next topic, which is the input impedance. So what is input impedance? Input impedance usually refers to the impedance that you're looking into transmission line circuit. What is the implication of impedance? 阻抗的意义是什么 Well, you should, I would recommend you to memorize it as the ratio of voltage over current. Then what is the difference between impedance and resistance? What is impedance? Impedance is usually written as Z, right? And it equals to what? R plus JX. So it contains two parts. OK 写的糊就表示我没有把握 OK resistance and reactance. So impedance is the sum of the resistance and reactance, which are the real part and the imaginary part of the impedance. And as I mentioned earlier, impedance, the definition or the physical implication of impedance is the ratio of voltage over current, right? So if the voltage and current signal are in phase, they have the same phase, then the division will be a real number. Then the impedance of the signal, which is a real number, can be referred as is the same as a resistance. Okay? If the impedance is an imaginary number, then the implication is the voltage and the current signal looking into the transmission line are not in phase. They have a certain phase difference. If the voltage is leading the current, then you will have impedance with positive reactance. I mean, if you draw the impedance on a complex plane, so you have resistance on the real axis and reactance on the imaginary axis. If the reactance is positive, then the impedance is said to be inductive, or the reactance of the impedance is inductive. 电感性的负载。On the other hand, if the reactance is a negative number, then it will appear on the bottom half of the complex plane. Then this impedance will be referred as capacitive loading. Or at least the reactive part of the impedance is capacitive. I suppose that you already know that in your circuit theory courses. So we are talking about basically just 电路的部分，电路学的部分，circuit theory. Okay, so let's go back to the transmission line circuit. So to the right is a short terminated transmission line. And of course, if you look into the short termination at the position of d equal to 0, which means you are looking just at the very right end of the transmission line, what is the impedance you observe? Well, that would be 0. The input impedance of the short termination, of course. However, you can still have the input impedance at a position away from the termination, which means you can observe the voltage over current ratio at any position on the line. So we would like to have a general expression for Z as a function of D. So to know that, we know that Z, the input impedance, is the ratio of voltage of current. So to have the expression for Z, we should do what? We should observe the expression for VD and ID, the voltage and current expression. As we have observed in earlier lectures, we know that the total voltage, which includes the V plus and V minus voltage, the forward going and reverse going voltage. the sum of the forward going and reverse going voltage for short terminated line can be expressed as VD equals to 2 times JV plus times sine beta D. So the variation is a sine function. As we already know that at a certain positions, you will have a 0 voltage, and at a certain position, you will have a larger voltage on the line. And the sensing can be can be done for the current distribution. So ID, the current as a function of position D, can be expressed as 2 times V plus divided by Z sub 0 times cosine beta D. So it's also a sinusoidal function. It's also a sinusoidal function for current distribution. However, if you do the division of the two expressions, that is, according to the definition, the input impedance Z is the ratio of V over I, then this function becomes a tangent function, right? You have a tan sine beta over cosine beta. So it's basically, it becomes J times Z sub 0 tangent of beta D. So what is the variation of tangent beta D with various D values? Well, tangent beta, a tangent function, what is the range of a tangent function? For cosine and sine function, the range is minus and plus 1, if you want to have real solution. But for tangent function, the value can be minus infinity and infinity. So it can be anything. It can be anything. Not that. So if you draw equation 7.13 on a plot like this, the horizontal axis is what? Is frequency. And the vertical axis is the input impedance. And we know that this is a pure imaginary number, right? Except what? Except at the position of beta L equals to 0, beta L equals to pi, 2 times pi, 3 times pi. When beta L equals to multiple of pi, then the tangent of this parameter will be 0. Okay? So when beta L equals to multiples of pi, the input impedance is 0 and it's not an imaginary number. Otherwise, the input impedance of a short circuit line is purely imaginary. Okay. Then, and we can tell that half of the time or half of the frequency, the Z-in, the input impedance, is the reactance of the input impedance is positive. It stays on the upper half of the complex plane. On the other frequencies, the input impedance stays on the bottom half of the complex plane. So they are referred as capacitive. So on the top half, it's the input impedance is referred as inductive. And in the bottom half, the input impedance is referred as capacitive, 电感性跟电容性. And at the position of quarter wavelengths, at the position of quarter wavelengths, the input impedance becomes infinity. It becomes infinity. So this is a very interesting property about short-ended transmission line. So according to plot, this suggests you can synthesize any reactance using a third short-terminated transmission line. You only need to adjust the length of the short-terminated transmission line to create any reactance. You can have positive one, the inductive reactance, and you can have negative ones, and refer them as capacitive. And the most interesting thing is if the length of the transmission line happens to be a quarter wavelength. If the length is quarter wavelength, then the input impedance here will be infinity. It's a short terminating line. So if you move from here, the input impedance is 0. If you from a certain distance, I mean quarter wavelengths away from the short termination, you end up with an open circuit. So this is quite helpful, or this is quite helpful in terms of microwave circuit design. So you can create any value, any value of reactance you want using just a section of short terminated transmission line, which will be referred as short stop in following sections. 我们之后会蛮常用到这一个技巧的了也就是 short stop 就是短路的那个终端短路的一个传输线那一小段你会看到它需要的距离你只要做到无限大的输入阻抗的话，你需要1/4个波长然后到了1/2个波长之后，它就会重复发生所以那一个 stop 的长度最多就是半个波长所以在半个波长内，你可以创造出任意的电抗值可以是正的电感性负载，或者是负的电容性负载那换句话说刚刚我们看到，对一个同样的一个频率，对一个特定频率的讯号来讲，那个传输线的终端短路传输线的长短会产生不同的 input impedance。但你只要换一个方式去想，就是说你去改变的是你是一个固定长度的终端短路传输线，但是你用不同的频率去测试它在不同的频率底下去看，你看到的输入阻抗也会不一样所以同样的一段的 physical size 一样的传输线它的输入阻抗是会随频率去变动的所以同样这个图你可以从变动长度的角度来去看也可以从变动频率的角度来去看。那你会看到说，在不同频率或不同长度底下，它所看到的输入阻抗是不一样的So the input impedance, the input reactance is 0 for values of the frequency equals to multiple of Vp over 2L. That is the frequencies for those frequencies. the length L equals to multiples of half wavelengths. We know that the input impedance of the short terminated circuit will repeat itself with a period of half wavelengths. So if the length happens to be multiples of half wavelengths at those frequencies, then the short terminated transmission line can be viewed as short circuit. On the other hand, the input impedance is infinity when the value of frequency equals to odd multiples of Vp over 4 times L, which means the length happens to be odd multiple of quarter wavelengths. That is 1 quarter wavelengths, 3 quarter wavelengths, 5 quarter wavelengths. So for those cases, the current at the input end of the transmission line will be 0. Then the equivalent input impedance will approach infinity, which is equivalent to an open circuit. So for the same short terminated transmission line, the same observation position, the input impedance will vary as the frequency changes. Okay, so which means so you can use this plot and moving on the line at a different position. If you observe the input impedance at this place, if you observe the input impedance at d equal to 0, that is the right end of the transmission line, then the input impedance will be 0 over infinity. So you will have 0 input impedance. And if you are quarter wavelengths away from it, then the input impedance becomes voltage V over 0. Over 0. Then you will have infinite input impedance. Infinite input impedance. And for example, here you are 1 wavelength away from the short termination, but at that position, the voltage becomes 0 and the current is in its maximum again, so the input impedance becomes 0 again. Okay, so every half wavelength, the input impedance will become periodic in a period of half wavelengths. 所以每半个波长它就会重复发生一次了哈。So the next question is, what can we do with short circuit light? What kind of application can we have with this short-ended or open-ended transmission line? So in the textbook, it discusses two kinds of applications. One is the determination of the location of a short circuit. Well, this sounds a little bit trivial, okay. So you want to know where is the short circuit position, or what is the length of the transmission line. So let's take a look at the example. So we have a generator connected to the input of a short circuit line, or open circuit line, but you don't know that. So suppose we are connected to a short circuit line and we vary the generator's signal frequency upward. Of course, you can do that downward. And the current drawn from the generator will undergoes maximum current magnitude and minimum current magnitude alternatively. Why? Why? Because the input impedance observed by the generator will vary between 0 and infinity as you change the frequency. So at a certain frequency, you will draw maximum current. You will draw maximum current due to what? Due to 0 input impedance. But at certain frequencies, you will draw minimum current because of infinity input impedance. Okay? So the maximum and minimum happens at the input impedance equal to 0 and infinity. And because the difference between a pair of consecutive frequencies for which the input reactance values are 0 and infinity is Vp over 4L。好了，我现在我没有，大家不用去强记啦，不用去强记什么 Vp 除上 4L 这一类的东西啦，但是你大概要记得就是，就是同样那一段线啦，在某些频率里头，它看到是输入阻抗为0，然后某些频率看到输入阻抗为无限大，而这个频率的间隔是固定的，那个间隔是这一个 expression， 然后 Vp 也是固定的嘛，所以从那个间隔，因为 Vp 是固定的，然后间隔是你观察到的，所以用这一个关系式，你可以去计算它的长度。事实上就在这里啊，在这里。OK， 所以电要用的式子其实是右边这一个啦 ，delta F 等于 Vp over 4L。The difference between maximum current and minimum current equals to Vp over 4 times L. So this expression can be modified a little bit to show that the length of the transmission line equals to Vp over 4 times the frequency difference. So let's substitute a few numbers. For an air dielectric line, what is the implication of an air dielectric line? Which means the transmission line uses air as its dielectric. So the velocity of propagation is what? 3 times 10 to the 8th. 3 times 10 to the 8th. So the air dielectric line tells you the velocity of propagation of on the transmission line. It's found that as the frequency vary from 50 megahertz upward, the current reaches minimum at 50.01 megahertz. So it's dialed up by 10k hertz, and then followed by a maximum current at 50.04 megahertz. So we need to determine the distance L of the short circuit line from the generator. So we simply substitute those numbers into these expressions. So the maximum, so the difference, the frequency difference in maximum current and minimum current is what? 30k hertz. 30k hertz. And so this is 30k hertz, okay? And we know that Vp equals to 30 times, Vp equals to 3 times 10 to the 8th. And 好了，我们不是用这个式子，我们是用的是这个式子啦。So 3 times 10 to the 8th divided by 4 and divided by 3 times 10 to the 4th, and it ends up as 2500. So this transmission line is 2.5 kilometer long. Okay. So this is a relatively long transmission line. Okay, the next thing. The next thing is a little bit interesting. So see if you can figure out how it works. The input reactance of a short circuit line of a given length can be either inductive or capacitive. So you can change the length of the short circuit line so that it can behave as an inductive load or a capacitive load. And you all know that to create a resonance, the simplest way is to connect an inductor with a capacitor. We refer it as the LC resonance, right? LC 一个病人的 LC 电路的话，就可以给你一个共振。好，那个共振频率可以从那个 L 值跟 C 值来去决定。所以，既然传输线它可以呈现电感性，也可以呈现电容性，那你把一个电感性的传输线跟一个电容性的终端短路传输线接在一起。好，那个日本那个唱什么 Apple 盘 Apple 歌的那个日本艺人叫什么名字？忘记了哈。你就事实上就是左边一段电感性的传输线跟右边一段电容性的传输线，把它插在一起，那一个传输线它就有一个自然共振频率。但你要注意的是你的观察点必须落在这里。好，从这里往左看是 L， 往右看是 C。Well， 那你这个地方就有一个 LC 共振了嘛。So let's consider the system as shown in the figure below, which makes up of two short circuit transmission line sections of characteristic impedance Z sub 01 and Z sub 02. So this is a more general case. So the characteristic impedance of the line on the left and the characteristic impedance of the line to the right can be arbitrary value, and so is the length of the two lines. So are the length of the two lines, as well as the phase velocity. And to create a resonance, we are supposed to have an inductive reactance. We intend to connect the two lines with one side with inductive loading and the other side with capacitive loading. Okay, so as you can see here, the two lines are connected in parallel, so we can find out the relationship of the voltage and current relationship on the two sides in terms of what? Admittance. Okay. 所以我们这边补充一下哈。这边我们看到 impedance 是等于 Z 加上 Z 等于 R 加 JX 哈。那 admittance equals to G plus JB。有没有看过？啊？我们写错，减 JB 吗？是哦，是吗？应该是都可以啦，好吧，反正是吗？我再查一下，反正我们后面会碰到哈，所以 Y 称之为 Y is referred as admittance, G is what? Conductance. What is the name for B? susceptance. Susceptance. Okay, let's take a short break before we come back to the final topic of section 7.1. So as we know that you can use, because the short-ended transmission line can be adjusted to arbitrary inductance and capacitance, so we can connect two short-ended transmission line in parallel so that the inductance and capacitance on the two lines can form an LC resonator. And the reason why you can have an LC resonance, or to determine the resonant frequency of such an device, we will also resort to the boundary condition. So for the figure on the bottom right, the boundary condition that you need to satisfy is at the interface, at the boundary between the two lines, the voltage must equal, and the total currents must equal to 0 as well. So, well, you can think of it as the result for KVL and KCL principles. So we know that the voltage to the left and the voltage to the right are the same. So you have V1 equals to V2. The total currents on the node, on the interface, must equal to 0. So I1 plus I2 equals to 0. Not that the I1 direction is defined going into the transmission line. So I1 direction on the bottom is pointing to the left, and the I2 direction is pointing to the right. And because the two lines are made of transmission lines, so the currents I1 and I2 can be replaced with voltage divided by characteristic impedance, or can be expressed as voltage times characteristic admittance. Characteristic admittance. Now, because the two transmission lines are connected in parallel, so it's easier to express the effect in terms of admittance Y. So you have the relationship of Y1 plus Y2 equals to 0. Okay. How do you get this equation from the top two equations? Well, you actually divided I1 plus I2. So you begin with I1 plus I2 equal to 0, and you divide both sides with V1. And because V2 equals to V1, so you replace the V1 here as V2. Then this becomes Y1, and the second term becomes Y2. So the summation of Y1 and Y2 must equal to 0. So to satisfy this condition, we know you need to have a positive admittance and a negative admittance, which means one of the line admittance is inductive and the other is capacitive. One is positive and the other is negative. So here is the expression of Y1 and Y2, which can be returned into the in terms of Z1 and Z2. We know Z1 equals to J times Z sub 01 times tangent of beta 1 L1. So you just simply substitute this relationship into here to have equation 7.16a. Not that beta 1 over here, not B1, beta 1. Beta 1 over here is replaced with 2 pi times F over VP1. So that's an a kind of a general expression. So you can provide, you can substitute with any characteristic impedance, any propagation velocity Vp for the two lines. So you can do the same to write down the expression for Y2, which is similar to the Y1 expression. And you know that Y1 plus Y2 equal to 0, so the sum of the two terms equals to 0. And to make the expression a little bit more easier, you times the two term with this, with the product of Y1 and Y2. So you end up with the expression, the equation 7.17. So we need to solve for equation 7.17 by knowing what? Knowing the length of L1 and length of L2. And in this equation, Z sub 01, Z sub 02, the characteristic impedance of the two lines are given. The phase propagation velocity of the two lines are given as well. And we want to solve, and L1, the L2, the length of the two transmission lines are known as well. So we need to solve for F, the frequency that satisfies this relationship, satisfies this equation. Okay, so let's check up with this using an example, all right? So in this example, let's assume the characteristic impedance is 60 ohm and 30 ohm. The one to the left is 60 ohm. The one to the right is 30 ohm. Okay? The length of the transmission line on the left is 5 centimeter. The one on the right is shorter, which is 2 centimeter only. The velocity of propagation on both lines are half of the speed of light. So it's c over 2. That is 1.5 times 10 to the 8th. And we want to obtain the 4 lowest resonant frequency of the system. Well, the question itself reveals that you have not only one solution for this parallel connection of two short-ended transmission line, right? And in fact, you have infinite number of solutions as the frequency goes up. You will have many solutions. So we only need to solve the 4 lowest resonant frequency of the system. 把最低的4个满足这一个关系式的频率找出来。要不要乘一下？ Okay, so by substituting the parameter, that is Z01 equals to 60, Z02 equals to 30, the length of L, and the Vp, and you substitute anything into here, you have this equation. And you know that this appears in the form of this. Tangent of kx plus m times tangent x equal to 0. And comparing the two equations, you can recognize that k equals to 2.5, m equals to 0.5, and x equals to this. Now, 0.08 times pi f over c. Now, c is 3 times 10 to the 8th. How to find out the solution of this equation? Well, there is no analytical solution, which means you cannot calculate the solution using pencil and calculators. 当然了，你可以用硬凑的啦，把数字硬带进去来去算哈。所以 所以它没有解析解了啊，没有 analytical solution， 没有 closed form solution， 所以你没有办法把式子整理成某一个式子，然后就找到 f 是多少，或找到 x 是多少。好，所以它没有解析解，但是没关系啦，我们可以怎样用暴力的方法来解它？好，怎么暴力方法来解它？把它拆成2条式子啊，然后把2条式子画出来，然后找这2条式子的交点，就是答案了。事实上，现在很多工程问题的解法其实都是这样干的，即便它有 analytical solution 但是用画图去硬干它其实是比较简单的啦。So in general, an equation of this type can be solved by plotting the two parts of the equation on the same plot, and the intersection of the two lines will be solution for this equation. So you separate the two parts of the equation as tangent kx and minus of m times tangent x, and you plus the result in terms of x. The horizontal x is x, and you can find out the intersection of the two equations. So you can program this expression with a computer and using tools such as MATLAB. 有多少人会用 MATLAB 的？会吧？要会用了因为不管你到哪一个学门学科，反正在电机领域里头多多少少会碰到一些讯号处理啊。那 MATLAB 就是一个高阶的电脑语言所以它跟人类语言很接近事实上几乎一样啦，你数学式就可以直接用 MATLAB 打出来了嘛，对不对？但是它求解的效率没有很好求解的计算效率没有很好，所以它是一个 general 的一个 tool 啦不是一个 specialized tool， 就像那个什么。就像你那个乌俄战争的时候，那些俄国的飞弹掉下来啊，你去拆一拆，里面都有一块那个 FPGA 嘛，对不对？它就是那个可程式化的那个逻辑电路板嘛，那个东西就是软体化的硬体，就根据你的需要你可以去把这一个 CPU， 你不能说它是 CPU 啦 ，FPGA 不能说它是 CPU， 但是它做的事跟 CPU 差不多，但是你要做 CPU 的话很贵吧 ？FPGA 也是要求贵啦，一块大概都几万到几十万台币的，一块 FPGA， 但因为军规的市场比较小嘛，所以那个一般都是用 FPGA 去做。我讲错，我讲到这个干嘛呢 ？OK 好啦，反正可以的话有机会的话还是要把 MATLAB 稍微了解一下它对于未来各位不管是哪一个学科都我认为都很有用啦OK, so you can write down the equation like this so if this program is written by myself. So the actual equation is over here. So if you wish, you can use MATLAB to type this code to generate this kind of plot. Okay. So the blue line is the equation for tangent kx. The red line is the equation for minus m times tangent x, okay? So the intersection are the solutions for the original equation. So what is the lowest frequency solution? Well, that would be this one. You may ask, why not this one? So what is the problem of this intersection? Well, this intersection appears at the position of infinity goes to minus infinity. So it's it's not a stable solution. Okay, so you probably cannot have a real solution at this position. Like it's just a transition region from infinity to minus infinity. Okay. So the stable solution can be found here. That will be your first solution. This will be your second solution, third, and the fourth solution. So they are found as 0.3, 0.55, 0.83, and 1.16 times pi. So the horizontal axis is multiple of pi of this thing. All right, so the solution for x is solution for this. According to this solution, you can find out the lowest for resonant frequency are 1.18, 2.08, 3.13, and 4.36 gigahertz. So you are recommended to play with this by yourself on your own computer. Okay.